A wave of itself is rather boring. I mean, if you went to the pond and you started taking a bob and bobbing it up and down, you would see something that looks like that. And we get that, right? We get that waves propagate out, that we would have some circular motion outwards and displacements. But really interesting things happen when you take two waves and you put them together. We get an interference pattern. The waves combine in some pretty interesting ways. And so the subject of this video is wave interference, and we're going to try and model that graphically together. So let me bring you on over to the whiteboard to our right. We're taking a trip, and we've got to our destination. So what happens when waves meet each other? They combine through superposition, which is when two or more waves that are traveling, they meet. The resultant wave is found by adding the displacements of the individual waves point by point. So I'm going to take three waves, A, B, and C. I haven't combined them yet, but I'm just going to look at these three waves and combine them in two different ways. One, I'm going to combine A and B, which are the same wave, just I'm going to put them on top of each other and act as if they were happening at the same time. Maybe an example I could give to this is sound. So if you have one sound with this particular wave and then you play the exact same sound in the exact same manner so that the waves are together in space, then we would get something like A and B. This is constructive interference. We'll see why in a moment. If I take, say, this point in space and I look at the displacement there and the displacement there, well, they're both positive and they would add together. So in this same space, we would have twice the displacement of that point and that point because the waves are on top of each other there. And for any given point, I could look at this point or that point or this point or that point. I'm going to choose to look at the very top. And I've labeled my amplitudes here, A and A, so when the two waves, A and B, are played on top of each other, we would see an amplitude of 2A. The same goes for at the bottom of the wave. They both have the amplitude A, so this is something I just labeled negative A. So the wave down here would be negative 2A because the waves add together at every single point along the wave. If I were to instead take A and C and put them together in space, you should see destructive interference. So at every single point, I could add this point up with the same point in space there, and if this was some value, I'll call it x, and this was negative x, well, they cancel out at that point in space. And for any given point, say we're looking at this point here in space, this is negative A, that's A, they both cancel out, we have no wave here. So we could have constructive or destructive interference, but it could be a mix of them. It won't always work out so nicely as to perfectly cancel out or perfectly align because they're the same wave. We might have something that looks like this. Let's take a trip back to the main board. I didn't make a road trip playlist, sorry. Alright, so here are some waves that are coming at each other. I've got these two waves. They have similar amplitudes and they come towards each other, and this is at one moment of time. So I'll call this at one point. As they're still coming closer to each other, just the fronts have interacted with each other and caused this dip here. So if you added up the displacements as these things came towards each other, we would have some slightly higher displacement here. But notice that the amplitudes haven't interacted yet, so we still have the same amplitude. But down here, a moment later in time, now the amplitudes are right on top of each other, so the total wave adds to itself, and we have this. So this would be something like 2a if that was A and A. We still have the same waves. Now they're just moving continually past each other. So we now get this wave that was formerly on the right side, now is on the left side. And it's separated from this one wave. Over here in the example B, it's the same deal, except this one is inverted. So when they come together, we have the moment where they first meet. When they overlap, completely cancel each other out. There's destructive interference. And then we get the wave that comes back out. So this wave on this side is now to the right of our wave that was moving this way. And then our waves go happily along. It doesn't necessarily have to look like a sinusoidal wave. Maybe we are given something that looks like that. It's a disturbance. Here's our disturbance. We will still analyze by superposition. We take a point and we say, all right, if the waves are starting to cross, then I'm going to add that point to that point. Then a moment later, I'm going to add that point to that point. And I would see these waves start to interact and form that sort of shape. And as the waves continually move through each other, I would have, when they're totally on top of each other, that sort of shape. I don't even know how to describe it. I just want to give you guys some familiarity with wave interactions. They're constantly moving. They move towards each other. They interact. They combine by superposition, and then they pass through. The last image that I wanted to show you is if you take a rope and you hook it onto some sort of end. The two ends could be either fixed or they could be movable, like a ring. If I take my rope and I flick it so I get this partial wave, it's moving towards the fixed end, it's going to hit the wall, and then it's going to bounce back. Because this rope here is applying a force onto the wall, and by Newton's third law, for every force there's an equal and opposite force. So if this force is up on the wall is going to supply a force downward onto the rope, and it reflects the wave like this. If there's a fixed point to the rope and the wall, so this thing cannot move. But if we look over at a movable ring, if you do the same exact thing, you flick the rope so you get this wave traveling this way, our ring can now move, so it's going to move up, and it's going to supply that same sort of flick back on the rope so it goes in that direction with the same velocity. Okay, hope you learned something. I will see you soon. Bye.